Assalamualaikum and hi everyone, I'm Faranza Shawafa. I'm in group 7. I'll be the first presenter for our group. Our group title is Electronic Portable Imaging Devices, Dosimetry. Electronic Portable Imaging Devices, Dosimetry, is usually used for patient setup during radiotherapy session. Advances in external beam radiotherapy have increased the accuracy requirement for dose delivery to patients. Therefore, quality control in radiotherapy is needed before and during treatment so that we can ensure a high level of accuracy which necessary for treatments design. The purpose of conducting a quality control is to achieve adequate tumor control and reduce normal tissue complications. Quality assurance procedure in radiotherapy generally demands dose measurement as well as patient positioning check. Thus, electronic portable imaging device plays an important role in quality assurance for modern radiotherapy. For example, IMRT, intensity modulated radiotherapy. Like the image attached here, the LINAC machine, the LINAC modalities. Okay. So the roles of electronic portable imaging device, the role of this dosimetry in quality assurance are for patient positioning and for portal dosimetry. In previous study by Franken, he stated that Epid based portal dosimetry became important for its fluence delivery verification purposes. For such dosimetry applications, an accuracy level of the portal dose as derived from the electronic portal imaging device measurements to within 1% to 2% is desired. Okay. There are two types in this presentation. In this study, we'll be presenting two types of electronic portable imaging dosimetry, which camera-based Epid and MFS silicon-based Epid. Okay, these two types of two-dimensional imaging electronic portable imaging dosimetry, Epid dosimetry system. For the first one, the camera-based particularly well suited for absolute dosimetry. This is due to their excellent response stability, response linearity characteristic, fast readout, and lack of ghosting. Okay. So, response stability means that if an Epid image is obtained for a given fluence distribution strike on the fluorescent screen, the corresponding image pixel values do not depend on time, only on the absolute values of this fluence distribution. Okay. The response stability of the based on the previous study, the response stability of the camera-based electronic portable imaging dosimetry device has been demonstrated to be within 1% to 2% over periods up to 1 year for various type of CCD cameras. Okay, so I show you here. This is the schematic illustration of the camera-based electronic portable imaging device, Epid with the X-ray detector. So we can see here, this is the detector. This is the radiation sources, which is the LINAC head. And then this is the detector. So So this is the schematic. This is the illustration how the camera-based Epids this is the illustration for the camera-based Epids. Okay, so the rest dosimetric properties, the dosimetric properties of these two types of Epids will be further explained and further discussed by my group mate. Okay, and then okay, for the next type, amorphous silicon electronic portal imaging dosimeter device, dosimetry. This type of dosimeter were originally designed for patient setup verification. However, this type of electronic portal imaging device function has been extended to dose verification over the past few years. This is because their portal images also contain dosimetry information. But previous study by McDermott, he stated that an amorphous silicon electronic portal imaging device, I'm sorry for the name is too long. Okay, so he stated that in his study that these amorphous silicon Epid are suitable for dose verification. The study shown that the pixel signal is approximately linear with the dose. Plus, the response of the amorphous silicon Epid is stable within plus minus 5% over long periods. Recently, amorphous silicon Epid has become the most commonly available portal imager. So, Okay, this is the configuration of the amorphous silicon electronic portal imaging device. Okay, stated in his study also, an amorphous silicon flat panel imager of iView GT Electa has 41 x 41 cm square detection area and very huge of the pixel, 1024 x 1024 pixels, and a touch guide, 1 millimeter copper build-up layer, a phosphor screen, this one, a phosphor screen. This is a copper build-up layer, a phosphor screen, and a hydrogenated amorphous silicon photodiode array. Okay, this photodiode array. Okay, so this is the configuration stated in his study. Okay, amorphous silicon based system. Amorphous silicon based system, within this unit, a scintillator converts the radiation into visible light. Okay, this is the radiation, and then the light is detected by an array of photodiodes implanted on an amorphous silicon panel. The photodiode later integrate the light into charge captures. So for amorphous silicon-based system, resolution and contrast greater than other system. Okay. Methods of Epid dosimetry, or the working principle of how it works. Previously I presented the working principle for amorphous. This how it works. The first by detecting the light, the scintillator converts the radiation first into the light, and then the photodiode here. I'm sorry, the photo is a bit unclear. So the photodiode, the array of photodiode. I'm sorry, where is my mouse? Okay. So the array of photodiode implanted on amorphous silicon plate, and then the photodiode later integrate the light into charge capture. So that is how basically the working principle. At least you can get the idea of the how it works. Okay, so for Epid dosimetry, okay, methods for Epid dosimetry. Epid dosimetry, first, verification procedure. Okay, verification procedure can be classified into two, which pre-treatment verification and treatment verification. So first, pre-treatment verification. Pre-treatment verification is a procedure comparing the whole or part of the intended treatment plan with measurement of corresponding radiation beams delivered by the linear accelerator outside patient treatment time. Okay, for treatment verification is a comparison of part of the plan and the delivered dose distribution based on measurement acquired during radiotherapy of the patient. Okay, these two measurements is used to determine the dose delivered to detector or to the patient. Okay, dosimetry methods. There are 4 dosimetry methods, which is non-transmission dosimetry, transmission dosimetry, in-phantom dosimetry, and in vivo dosimetry. Okay, dosimetry methods are independent of the type of detector used. Can be grouped according to whether or not beams have passed through an attenuating medium, or whether the dose is reconstructed inside a phantom or a patient. So first, for non-transmission dosimetry. Non-transmission dosimetry is a determination of the dose in the detector, which is the dose does not transmit. Wait first. Okay. Beam have not passed through the attenuating medium. Okay. Determination of the dose detector in the detector, patient or phantom, or determination of the incident energy fluence based on measurement without an attenuating medium between the source. Okay, sorry. Non-transmission, the measurement without attenuating medium between the source and the detector. So there is no patient. Later I will show the configuration for these methods. Okay, for transmission dosimetry, determination of the dose at the position of the detector, patient or phantom. Determination of the incident energy fluence based on radiation transmitted through the patient or phantom. So for the transmission dosimetry, there is patient or phantom. For non-transmission, there is no, the measurement done without patient or phantom. So for transmission, the measurement done with phantom or patient. Okay. For in-phantom dosimetry, measurement or determination of the dose inside a phantom. This type of dosimetry is rarely performed with Epids, but included for our extra knowledge. Okay, this can be the dose at points, lines, planes, or volume within the phantom. So for in vivo dosimetry, measurement or determination of the dose inside the patient. Measurement performed during treatment can be performed invasively, which is inside the patient, or non-invasively. For in vivo, non-invasively, which are at some distance from patient. Okay, for invasively inside the patient, non-invasively at certain distance from the patient, whereby the in vivo dose at the point of interest is obtained by extrapolation. Okay, Epid dosimetry and the use of dosimeters position on the skin of a patient belong to the second category of in vivo dosimetry. So Epid is non-invasive in vivo dosimetry, which is the dosimeter is placed at certain distance. It is not inside the patient. Okay, so this is the configuration for the methods. So the dose can be measured and determined at different locations with different configuration of the epid. Phantom or patient. Okay, different configuration, like different configuration of epid, different configuration of patient or phantom. Okay, as shown in this figure. Okay, first, the non-transmission pre-treatment. Okay, non-transmission pre-treatment will acquire image for each field without a patient or phantom in the beam. Okay, like I said before, non-transmission, there is no patient or phantom in between the sources and the detector. Okay, so for the second case, non-transmission treatment dosimetry. Okay, this is the pre-treatment. Okay, this is during the treatment. Okay, non-transmission treatment dosimetry. Acquire image for each field with the detector located between source and the patient. Okay, the detector located between the source and the patient during treatment. Okay, during treatment. So the detector usually attached to the linac head. Okay, here. Okay, the detector will be attached to the linac head. Usually during treatment, for non-transmission during treatment, the detector will be attached here. Okay, for transmission treatment dosimetry, transmission, the transmission. Okay, non-transmission is the phantom or patient is not in between the epid and the sources. Okay, for transmission, there is phantom or patient in between the detector and the sources. Okay, for transmission, the acquire image for each field with the detector located behind patient or phantom. Okay, like shown in this figure, this case, the epid is placed under. Okay, the patient is on the couch. Okay, this is the linac head, the sources, and then the detector will be placed behind, under patient or phantom. Okay, so this is the three arrangement for epid dosimeter. Okay, that's all for my part. Thank you.
Assalamualaikum and hi everyone. My name is Siti Nurhazika binti Hasim and I am from group 7. So my group get the topic of Epid dosimetry. So now I will continue and going to present on the symmetric properties of Epid dosimetry. Okay, so epid dosimetries have a variety of dosimetric properties that make them appealing to radiation dosimetry systems. So, dosimetric properties of epid dosimeter need to be investigated or learned for verifications of dynamic applications. Okay, so these are the properties, the dosimetric properties that I will be going to explain after this. So the first one is the dose linearity, and second one is dose rate response. Next, field size response, and lastly, the effect of build-up. Okay, for the first dosimetric property of the epid dosimeter is the dose linearity. So, a study carried out by Sukuma et al. In 2011 with title of A Study on Dosimetric Properties of Electronic Portal Imaging Device Epid and its use as a quality assurance tool in volumetric modulated arc therapy (VMAT). So in this study, the dose linearity of Epid in integrated mode at 300 mu per minute was demonstrated by irradiation with different monitor units from 2 up to 500 mu for field size of 10 cm times 10 cm at 100 cm SDD. Okay, here SDD is an acronym that stands for source to detector distance. Okay, the mean pixel value of 3 by 3 matrix at the center of the field was measured and a graph was plotted against monitor units. The unit of the electronic portal imaging device, which is Epid, is calibrated unit, CU. So CU can be calibrated as MU or grade or centigrade. So as we can observe from the graph plotted in this study that I have attached in these slides, the calibrated units was linear to the dose delivered or monitor units. So the graph shows the linear fit parameter, the R squared value that equals to 1. Okay, we move to the adjacent figure in these slides. Another study performed in 2007 by Gzazi et al. With the title of Epid Dosimetry, Configuration and Pre-Treatment IMRT Verifications. So the investigation's purpose was to calibrate the Epid and TPS and to evaluate the usefulness of that method for dose verification in intensity modulated radiation therapy or IMRT techniques. So throughout this study, the linearity of dose was also studied. The linear response was observed over the measured irradiation time range from 2 up to 300 mu for 3 tested accelerators. So the graph at the right is illustrated that Epid respond to the function of dose for different square field size, average for 3 measurements performed. So in conclusions, from both figures in these slides, we can say that when the monitor unit increase, the Epid calibrated unit CU is going to actually increase too. Okay, for the second dosimetric property of Epid dosimetry, which is the dose rate response. In the same study as I previously mentioned by Sukuma et al., the calibrated units CU for field size of 10 cm times 10 cm was measured for different dose rates. The CU values were measured for the 5 readings for each dose rate and an average value was calculated. This means that they repeat the same measurements and one dose rate for 5 times. So for example, for 100 mu per minute, the CU values are repeated for 5 times and after that, they calculated the mean CU. The percentage variations was calculated between the average value and average value of 300 mu per minute. This was shown in the table that included in these slides. Even though the calibrated unit is calibrated separately for different dose rates, the variation observed was found to be only 0.75%. Okay, next, move on to the next figure, which came from a research by Kurdi et al. Entitled Dosimetric Properties of an Amorphous Silicon Epid Used in Continuous Acquisitions Mode for Application to Dynamic and IMRT. So objective of this study was to investigate the dosimetric properties of an amorphous silicon electronic portal imaging device, Epid, operated in a real-time acquisitions mode. The linearity of Epid response in continuous mode was examined for three dose rates, which are 100, 300 and 600 mu per minute. The linearity of Epid central axis response for different dose rates is compared in this figure. So it is observed that linearity improved with increasing of monitor units. Incomplete capture of dose rate of those data may explain this behavior for all dose rates. The amount of dose delivered per frame at 600 mu per minute will be larger than at lower dose rates. Hence, this explains the increase of nonlinearity at higher dose rates. Okay, for the next dosimetric property for Epid dosimetry is the field size response. Okay, based on a study performed by Sukuma et al. That I was already explained previously, demonstrate the field size response dosimetry property of Epid dosimetry. The CUs were measured and the output factor was calculated for different field size and then plotted. Different field size ranging from 5 cm times 5 cm up to 27 cm to 27 cm field size. 100 mu was delivered at 100 cm STD. The CUs were measured and the output factor were calculated and plotted against the field size. The results obtained were compared with those of the ionization chamber measurements or IC measurement. The variation for 5 cm times 5 cm field size is 2.9% and for the 27 cm field size is 5%. This variation was due to the difference in the phantom scatter factor for both ionization chamber and Epid dosimeters. Since the scatter has a lower energy component, its effect on the Epid's phosphor response is enhanced compared to ion chamber due to the presence of high atomic number components in the phosphor. Okay, for the final or the last dosimetric property for Epid dosimetry that I will explain is the effect of buildup. A study was carried out in 2006 by Greer et al. With the title of Dosimetric Properties of an Amorphous Silicon Electronic Portal Imaging Device, Epid, for verification of dynamic intensity modulated radiation therapy, IMRT. So this research aimed to investigate the dosimetric properties of an amorphous silicon electronic portal imaging device, Epid, for verification of dynamic intensity modulated radiation therapy, IMRT delivery. The effect of added buildup that plays on the detector surface on the Epid dosimeter response for the 6 MV beam was investigated. So this was done in order to determine whether added buildup materials was required for a dosimetry to be accurate. So therefore, the results of these investigations were explained. So for 0, 0.5, 1 and 1.5 cm thickness of added buildup, the mean Epid pixel values were 99.4%, 100%, 98.8%, and also 94.7% respectively. Okay, this means that for 0 cm thickness of added buildup, the mean Epid pixel values were 99.4%. For 0.5 cm thickness, the mean Epid pixel values was 100%. Meanwhile, for 1 cm thickness of added buildup, the mean Epid pixel values was 98.8%. And lastly, 1.5 cm thickness of added buildup will contribute to the mean Epid pixel values of 94.7%. Okay, the signal is a maximum for an additional 0.5 cm of solid water and decrease for larger thickness. The Epid signal corresponding to no extra buildup is within 1% of the maximum, which means that it is very low. The maximum is at 0.5 cm that contribute to the mean Epid pixel values of 100% that I have explained just now. This is due to the inherent buildup provided by the copper plate and other detector components. The profiles for the open fields with and without the 0.5 cm of solid water buildup were also within 1%. So the difference is really low. So the effect of the extra buildup was only evident in a slight blurring of the penumbra. Therefore, no extra buildup was utilized in these investigations. Okay, that's all from me about the dosimetric properties of the Epid dosimeter. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Ainul Madia binti Nasruddin. I would like to present about the advantages and disadvantages of electronic portable imaging device. Advantages of electronic portable imaging device. First, fast image acquisition. Second, ability for in vivo measurement and 3D verification. Third, require little delivery dose as possible to obtain a high quality image which used for facial localization, and it do not require the setup of any additional equipment after the system has been installed. Finally, electronic portable imaging devices are attached to the gantry of linear accelerator, and they are sold with the majority of new accelerator purchased. Disadvantages of electronic portable imaging device. First, image quality strongly restricted by the low contrast and limited spatial resolution available. Factor that limiting contrast in photo image because the X-ray attenuation is dominated by quantum interaction at therapy energy as opposed to photoelectric interaction at diagnostic energy. Second, lower probability of interaction with matter compared to the lower X-ray energy in diagnostic imaging. As a consequence, the fraction of the radiotherapy beam that produce detectable signal in the converter called the X-ray quantum detection efficiency is commonly low, and contrast at higher energy is significantly smaller, which provide less information. The response of electronic portable imaging devices affected by the constant and lag. Finally, quality image be limited by the statistical noise of the X-ray quanta or amount of X-ray that are detected, compared to other competing noise sources such as noise from the acquisition system electronic.
Hi, I am Nid Nurul Afina and I will be presenting on the clinical application of the Epid. With the introduction of IMRT, the use for Epid for dosimetry have received more attention. So the question is, what is the use of the Epid in the clinical routine? The Epid can be used to verify the patient positioning. The geometry accuracy of patient positioning in IMRT technique is very important with the step dose gradient between the target volume and also the organ areas. The portal image obtained using the Epid panel will be compared with the DRR generated by the TPS. The overlay is the fused image of the DRR and also the portal image. The patient setup error was represented by the deviation of the compact bony landmark. The correction was done by the automatic adjustment of the treatment table in 3D before the application of the radiotherapy in every patient. So this is the example of the value of the table adjustment needed. Besides, the need for patient-specific QA also stimulated the use of the Epid dosimetry. Once the treatment plan is approved, it is sent to the record and verify system for the pre-treatment delivery. And the bill will be delivered to the Epid. The measured fluence map obtained using the Epid will be compared to the original treatment plan, and that's how we can use the Epid for the patient-specific QA. Lastly, Epid could be used to perform in vivo dosimetry in a relatively simple way during the treatment. So the figure shows the result of a verification of a 6-field IMRT plan for the esophagus cancer treatment. The comparison of the Epid reconstructed and the planned dose distribution showed a 1.5% difference. So, as a conclusion, for the clinical application of the Epid, there are 3 applications. First, the Epid can be used to verify the patient positioning. Second, for patient-specific QA. And lastly, for the in vivo dosimetry. These are the reference used for this presentation. And that's all from us. Thank you.